Hello everyone, I'm Vinay, a PhD student with McMaster University, and today I'll be talking about xerographically patterned gold leaf contact electrodes, which were used to demonstrate a flexible chemiresistive sensors. Flexible sensors are used in different applications like medical diagnostics. They are commonly used in wearables, which you might have seen like Apple Watch bands, and they are also can be used in environmental monitoring to monitor um, different parameters like water quality, and typically they can be used on different curved surfaces, and they finally can enhance the integration of these kind of devices in complex environments. Currently, these conductive electrodes are fabricated by common methods like sputtering, where a metal target is used to deposit a thin layer of required metal on the substrate. This method particularly requires a sophisticated instrument and very controlled lab-based environment. So this can be expensive to operate also. On the low cost end, we have methods like screen printing, which can be done anywhere. But here, depending on the inks we are using, we we can get some inferior sensor performance. And if we're using inks which are superior for sensor performance, the sensor can be expensive. And it also requires multiple steps to fabricate the sensors. Therefore, our objective here is to provide a low-cost alternative to make flexible sensors, and we have demonstrated this by solid-state chemiresistive sensors. And for this purpose, we are using metal leaf, and for the sake of study, we are using gold leaf as an example. So what are gold leaves? These are very thin gold sheets with thickness like 100 to 140 nanometers. Commercially, these gold leaves are available and used as a gilding material for different purposes like decorations, paintings, etc. This offers a low-cost alternative because 8 centimeter by 8 centimeter sheet of gold leaf can be bought at around $3, which can give us multiple gold electrodes. But the major problem with these gold leaves is they are very fragile and they are very difficult to handle and direct patterning. So here we propose a direct patterning of gold leaf method. So to start with, we generally use a single-sided tape to fixate our gold leaf on top. Once the gold leaf is fixated, we will cover this gold leaf surface on top using paraffin, which is further going to protect the gold leaf when we are patterning it using a benchtop tabletop cutter. That we are using this tabletop cutter, it's because it's also a low-cost tabletop cutter, which can be bought somewhere close to like $300. And finally, we can generate, this method can be used to generate different patterns like curves, patterns like as shown in the picture. So we have used this method to fabricate chemiresistive sensors for free chlorine. Free chlorine is typically used to disinfect drinking water supply and water used for different recreational purposes like swimming pools. So what exactly is chemiresistors? Chemiresistors are a simple setup for simple set of electrodes which have three main components. The first one is sensing material, which is the active component of the sensor. When analyte binds on top of the sensing material, the resistance of the sensing material is going to change, and this signal is picked up by these conductive connectors. We have a very small voltage supply. Here, typically in our case, we generally use 10 millivolts as our signal, as our supply, and we collect current as our output. And as soon as the analyte binds, we are going to see a resistance change, which is again shown in the change in current of the sensor. Here, the sensor fabrication is done used on a Kapton tape, which provides a flexible substrate. On top of that, we have used the sensing material as graphene like carbon, which were in sheet format and which was again patterned using xerography. And finally, the gold leaf was put on top of the sensor to make the electrical contacts between the GLC sheet and our final electrical connections, which were made using copper tape. Finally, the sensor area was fabricated using a parafilm, and our defined sensing area was defined. The sensor works. We load the sensor with an active molecule called PCAT, which makes it selective to species like free chlorine. So in presence, so when the sensor is loaded with PCAT, we'll typically see a reduce in current because of reduction in number of conductive pathways between the single or carbon nanotube network. Once we'll have free chlorine due to electron doping, due to doping effect, we can see an increase in current, and this reduced PCAT is converted to oxidized PCAT, and we can see an increase in current in the sensor, which is correlated with the amount of free chlorine present in the solution. As you can see in this case, we have exposed the sensor to 5 different free chlorine concentrations, and you can see the sensor kind of saturated at the last concentration, but we can still measure the free chlorine concentration till that point. Finally, we have shown the impact of bending on these sensors. So with gold leaf, as you can see, all the sensors survived post-bending after 15 cycles till 120 degrees. And the chemical sensing response of the sensors were very similar. While in case of screen printing, even though it looks like the sensing response is very similar, out of 3 sensors, 1 sensor failed. And the major difference here you can see is my current change. My overall current change is less for screen printed carbon sensors. Even though they are low cost, the sensor performance is lesser as compared to these gold contact electrodes. In terms of interferences, we have also tested the interferences with common interference like sulfates, nitrate, chloride. And as you can see, the sensor works pretty well as compared to free chlorine response. So in conclusion, we have shown a low-cost rapid fabrication method for patterning leaf to make thin metal sensing electrodes. And here we have used this method to fabricate a flexible chemiresistive sensors, where we have used metal leaf as contact electrode. And we have seen that majority, like most of the sensors here, showed no effect on sensing response with multiple bending cycles. In this case, we have done till 15 bending cycles up to 120 degrees. But the major drawback of this patterning method is we can just generate patterns which are conductive on single side, because in most of the cases on the opposite side, we have a PET liner. The second drawback of this particular sensor is basically we need a baseline reading. As most of the cases you have seen, we are reporting the conductivity change. So these kind of sensors are going to have that as a major drawback. Group. Thank you for listening.